students, welcome to the chemistry sessions. So I hope everybody is doing great. Now, in the last session what we have discussed? We discussed something very interesting, and that too something about how we can form the salts of oxoacids for the alkali earth metals, right? And those salts which we have discovered were sulfates, carbonates, bicarbonates and nitrates. We discussed all of these, right? So they were sulfates, carbonates. In fact, just for an extra information, I told you about the bicarbonates as well. Yes. What else? The last one was the nitrates. Can you give me quickly any single preparation of each one of them? Sulfates. Why a sulfuric acid? I need to put sulfuric acid anywhere, right? Not on yourself, but any kind of an alkaline earth metal, right? A pure metal I can take, or I can just take its oxide or hydroxide or carbonate. My work is done. Sulfate, done. Carbonates. Remember the lime water test? If you remember the lime water test, you will be remembering how to form the carbonates as well, right? So in the lime water test, what we did? Calcium hydroxide, pass the carbon dioxide, and we get is the carbonate, the limestone. So here also MOH whole twice plus CO2. What are we getting? We will be getting is MCO3. Fine. And yes, there is another method of preparation for these. What is that? Is if we take up any soluble salt, just mark this, it's important. Soluble salt of alkaline earth metal, AEM, alkaline earth metal. So any kind of a soluble salt. Let's say if I take up, right, calcium chloride, it's soluble in water, making it react with ammonium carbonate, right? Or what I can take is sodium carbonate also. This is another preparation, and yes, this is important. What we will be getting is the one I desired, that is calcium carbonate is my main product, and that is what another preparation for the carbonates, right? Now comes up the bicarbonates. In the bicarbonates, what do I have to do? Again, remember that reaction for the preparation of baking soda? A similar kind of a reaction will be followed here. So it's like a carbonate we have to take, MCO3, pass the carbon dioxide in a solution of that. What we get is MHCO3. Don't forget the oxidation state so that you form the complete formula. And the nitrate via what? Via we have to take is the nitric acid, HNO3, and we can take up is, let's say it's hydroxide, it's carbonate or whatever it is. Let's say MO, this time I am taking up is MO, oxide. From oxide I need to form, I can form it very well. It is also possible. So that was the thing which we discussed in the last session, along with the very important things. Do not think that these are not at all important, but these are the only things which are important. Is the solubility, which is mostly coming in the exam, right? From the exam point of view I am telling. And the thermal stability. So here's a question for you, that why sulfates and the carbonates, they have got low solubilities when we go down the group. So the question is, why sulfates and carbonates? Yeah, this question is straight away from the NCERT. Why sulfates and carbonates have low solubility? In fact, almost insoluble they are in going down the group. I am not writing the entire question. Down the group. Fine. So the answer lies in the hydration energy and the lattice enthalpy. Both of them decreases, right? So you need to write is that both lattice enthalpy and hydration enthalpy decreases. Fine. When moving down the group. But what happens is, this is lattice enthalpy Le, right? The decrease in hydration enthalpy is much more than the decrease in lattice enthalpy, and this is the complete answer for this particular question. Clear? Now here's another question for you that I have to ask you, right? I have got, we have discussed about the sulfates, we have discussed about the carbonates. Here there is hydroxides. Remember the basic hydroxides we have discussed. So the hydroxides, on going down the group, their solubility decrease, right? I need the reason for this. So that is a question, and tell me the reason for that. So the reason you must be thinking is a similar, that the decrease in the hydration enthalpy is much more than that of the lattice, right? But it's not like that. It's the other way around. For the hydroxides, always think opposite, right? So here is, both are decreasing. Both are decreasing, right? Ongoing down the group, right? So on going down the group, both are increasing. What both? The lattice enthalpy and the hydration enthalpy. Fine. But the thing is, both are decreasing, this is also decreasing, this is also decreasing. But it's the other way around, as I told you, it's just the opposite. So the decrease in the lattice enthalpy, decrease in Le is much more than that than the decrease in hydration enthalpy, right? So it's the other way around on going down the group, although both of them are decreasing. But here the decrease in the lattice enthalpy is much more as compared to the hydration enthalpy, and that completes the answer. So in the case of hydroxides, the difference now you know. Clear? So let's move on to what we have to discuss today. It's the anomalous behavior of beryllium. Why beryllium is behaving so differently in the entire group, right? What is the reason behind that? So let's study about it. So it's a somewhat similar reason to what we have observed in the case of lithium in the alkali metals, group 1. So can you think about those reasons first of all? Similar kind would be observed in the beryllium as well. So first of all, the reason for the anomalous behavior of beryllium, reason behind it. So the reason is, first of all, the very small size of beryllium, in fact smaller than the lithium. So you can now imagine that why beryllium is so much differently acting, right? So basically is the small size of beryllium, right? And due to this small size, what do we have is highest ionization energy in the entire group, or just the high ionization enthalpy or energy in the group, right? Now comes up another point. Do you remember the points which we have discussed in the lithium case? It was, one of them was vacant d orbitals. Yes, that is also applicable over here, that non-availability of vacant d orbitals. You know what the problem with beryllium is? It has got 4 electrons, right? And if I talk about the valence electrons, these are just 2. So beryllium is always electron deficient, right? It is handicapped, right? It is electron deficient. It has no choice. Why? Because it does not have any accommodation space to allow the electrons from external agent to come into it, to fit into it, right? It can only form 2 bonds at max. At max, if I talk about the pure compound which it can form, it's only the 2 bonds, right, and nothing else. So basically, it's a handicapped, it has got a problem with it. One choice was to accept electrons from some external agent to make a molecule, to form a bigger molecule, to form a bigger complex, that too having a bigger structure, so that it is able to accommodate all the anions around it, and those anions will be donating it, will be neutralizing its deficiency, right? But it does not have any option because it has no vacant d orbitals present, no accommodation space, no accommodation space, right? And since it does not have any accommodation space, it can maximum form up to 4 bonds, right? And one of their example is BeF4 2 negative, one of the examples. At max 4 bonds it can form. Yes, why I have represented this structure as the square brackets? It's another kind of a complex molecule which is formed, and you will be going to read about it later on in the 12th standard, no need to worry about that. So it's basically a coordination complex. Coordination complex, you must be finding this term very new, but yes, this is what it is. So the reason you have known: smaller size, high ionization enthalpy, non-availability of vacant d orbitals, and in fact compounds of beryllium, let's say hydroxide and oxides, right? They are what? They are amphoteric in nature. Right? Clear about it? So that is the basic reason. So the basic reason out of all 4 is these 3, first 3. This is not as such the reason, but you can say it's one of the evidences which will prove that yes, it is showing somewhat a different behavior from the rest of the alkali earth metals, right? Let's move on to the kind of reactions which it shows, right? So we'll be just recalling what we have done so far, that how beryllium is different. Try to find out the molecules which we have formed related to beryllium, and yes, you must have got it by now. So first of all, we will be discussing the behavior of beryllium, a little one. Beryllium. Whenever I hear this name beryllium, it reminds me of my cat because her name is Berry, right? So it's beryllium. I find this word really cute, right? So beryllium, it's a short one, it's a smaller one, it's a cute one, right? So basically, beryllium being small in size, being high ionization enthalpy, what it has got some peculiar behavior which shows in its nature of the compounds which it forms. So the compounds like beryllium oxide, whichever you name, beryllium hydroxide, BeH2, BeCl2, whatever it is, right? All of them have one thing in common. What is it? I have already told you this. So it's the covalent nature. So the first question and question number 1 to 2 will be of 1 mark, right? Remember this. Always remember the weightage of the question and then only try to answer. Do not just go on and elaborate and just write the entire thing which you know, right? They are not testing that how much you know, they are testing that how precise the answer can be, how accurate you can be, right, as per the given marks. So, what is the chemical formula of plaster of Paris? Give its one use. So, what is the another name for plaster of Paris if I talk about in chemistry terms, in chemical terms? So, it is a layman word basically, right? It is also known as plaster of Paris. So, basically it is calcium. So, it is pretty easy question. Calcium sulfate, hemihydrate, yes, and it's formed from gypsum, you know this. Now, it is CaSO4 dot half H2O, clear? So, that is what the plaster of Paris is, and they are asking give its one use. One use, you know, it can be used for building materials, it can be used in medical purpose, right? For medical purposes, just for immobilizing, if let's say I have got a fracture over here in my hand, so the plaster of Paris, there will be a covering, a mold which will be covering my entire hand so that it gets immobilized and the bone will get repaired, fine. So, in all those cases these are used. I hope everybody is clear with it, and any one of the use you can write because they are just asking one use, right, as per the marks. 1 mark, half mark for the formula, half for the use, clear? Let us move on further. So, what do we have in the next question? Yeah, why do we store sodium metal in kerosene oil and not in water? So, you know this. Why it is stored in kerosene oil? In order to cut the supply of air and water, both. So, what happens to the sodium metal basically whenever it tries to react with water? What will happen? Explosions. It will catch fire. Why? Due to the release of whenever sodium reacts with water, the main thing which is released is H2 plus the other ions Na plus and OH negative in the water. And due to the release of this hydrogen gas, we know it's explosive one, it immediately catches fire if it comes in contact with the water and in fact the air as well. That is why we cannot just openly put the sodium anywhere. We need something to cut out these supplies, and that is can be kerosene oil, can be wax, right, waxy substances, so that the entire wax or the oil, it surrounds the metal and it does not get in any contact with the water or air, right. So, in chemical terms, it is, the main reason is due to the release of the hydrogen gas, and yes, in layman terms what we can call it, it is vigorous when it reacts with water or air, clear? Explosive or vigorous or violent reaction you can say. Fine, let us move on. Okay, what do we have in the next question? Question number 3 to 4, 2 marks. Arrange the following sulfates. Okay. Now, we have discussed about sulfates, carbonates, nitrates, we have discussed about hydroxides. So, these 4 are very, very important, fine. Any question can arise, can come up from this topic, right. So, what I have got here is something related to sulfates of alkaline earth metals. In the alkaline earth metals, we have discussed that in the order of decreasing thermal stability. Now, first of all, let me just write the sulfates over here. So, they already have given right. So, these are what? Alkaline earth metals, and if I try to have the sulfates of them, now down the group what happens? Down the group the thermal stability will increase. You know, whenever we are going down the group, the solubility is decreasing. Why the solubility is decreasing? Because of decrease in the hydration enthalpy. The hydration enthalpy, whenever it gets dissolved in water, the energy which is released is not enough to overcome the forces of the lattice enthalpy, right? And that is why it does not get soluble down the group as much, fine. So, it's the solubility decreases down the group, sparingly soluble while coming down the group, fine. And since the solubility, you can just remember it this way, that if the solubility is decreasing, that means it is not getting dissolved, right, in water, thereby it will be a stable solid compound, fine, and that is why these are thermally stable if we go down the group. So thereby thermal stability increases down the group. It's just the opposite, fine. And what is the main reason behind this thermal stability increase? It's the more electropositive character. Fine. More the electropositive character, more it will be a very good. See here, these are all ionic compounds, fine, and bigger the anion and bigger the cation, there will be a very good interaction between the two. So sulfate is itself a bigger one, and we get, let's say, barium, it's also a bigger one. So bigger and bigger will be a very good interaction in between. So due to this, they will be thermally stable. That means upon heating, they will not just like that dissociate. We will have to provide a lot of heat to dissociate them, fine. Now what will be the decreasing order? Decreasing means starting from the very highest. I have got the highest is, yeah, as per my series over here, I have got first is the strontium, then the calcium. This is the highest, second, third, and this is the least. Why? Beryllium is smaller size, sulfate is very bigger, so it will be again not a good kind of an interaction, right? It will be more of covalent as compared to the ionic character. Clear? So that completes my question number 3 as well. So I am not rubbing this off because this may be needed further. Now, which of the following has the highest solubility in each of the following? Fine. See here, we already have discussed in the case of sulfates, yes. So in the sulfates, Ba, barium, magnesium and calcium they have given. I need is the solubility as I am moving down the group, as I told you. Now the hydration enthalpy is not that much, right? I am not writing the exact reason for you, I am just telling you here. So listen carefully. So down the group, always the solubility is going to decrease due to the decrease in the hydration enthalpy, decrease in hydration enthalpy. So basically what is happening is down the group, lattice enthalpy as well as hydration enthalpy both are decreasing together. But the decrease in the hydration enthalpy is much more, thereby accounting for the fact that it is very less soluble in water. Clear? So what do I have here? Highest solubility out of the 3 I need to find out. So it's definitely the barium. This one first, right? Second one would be this, and third will be the least. Now if I talk about the solubility in the case of hydroxides, it's somewhat different. This is important. And this I have already told you in my session that in case of hydroxides, the order is opposite. In case of hydroxides, the solubility increases down the group, right? Because now these compounds, if I move down the group, see here, down the group will be barium hydroxide basically. So it's a bigger one, right? So we are not considering here which one is bigger, which one is not. So basically this atom, this compound will get easily dissociated in water, right? It, due to the bigger size, it will get dissolved in the water very easily, thereby giving more and more OH negative ions. So basically down the group the basicity is increasing. Down the group basicity is increasing, and due to the increase in this basicity, solubility is in turn increasing, fine. So which one will be having the highest? The highest, yeah, first of all, let me just, okay, move on to the first part over here. Have we done that correct or not? Which one is having the highest solubility? So I think I have written just the opposite of it, because here I have told you that down the group the solubility is decreasing. So the least would be for the barium, right? That means magnesium should be having the highest one, right? We just have discussed, I just have written mistakenly the opposite order. So it will be 1, then 2 and then 3. This one will be having the highest, fine. And here the order will be just the opposite. So always remember, in case of hydroxides, the order is just the opposite, which is barium must be having the highest solubility because it can give OH negative ions very easily, more basic. So 1, then 2 and then 3. Clear? So I hope everybody is clear with the fact. Now let's move on to the question number 5. Right. Okay. Let's just remove this. Now, how do the following properties vary among the alkali metals? So it's a simple question, just the general idea we have to give. They are asking about alkali metals. What are alkali metals? Group 1. So it is Lina ki Rab se friendship. Yes. Lithium, sodium, potassium, rubidium, cesium and francium. Fine. Atomic radius. Now, how do you account for this atomic radii? Atomic radii, since it is the group 1, the very first series, fine. So it will be having the highest atomic radii first of all, highest in period, fine. These are having highest atomic radii in period. If I move down the group, what will happen? Again, due to the increase in the atomic number, there should be more of nuclear charge and there should be a decrease if I go down the group. Whereas, due to the addition of more and more shells and due to those adding shells, what will happen is, there is shielding effect going on, yes. Due to the inner shells, there is more shielding effect, fine. And due to that shielding effect, the size is thereby increasing down the group, right. Counteracting with that of the increasing nuclear charge, we have got a shielding effect in between, and due to which the size is in turn increasing instead of decreasing down the group, fine. So here atomic radius or radii increases down the group. Here they were small, now this, like that, it is increasing, fine. And that is how the atomic radii is increasing, and they have got the biggest if we talk about the entire period. Clear? Done. Ionization energy. Ionization energy again based on the atomic radii, right? So down the group, ionization energy, it is decreasing because more of the size, it will give away the electron, the free electron, that is only 1, right? So lithium has got configuration 1s2, 2s1, yes, and similar will be only 1 electron is there to lose, right, to attain the stable noble gas configuration. Down the group, ionization energy decreases because of the bigger size, it is willingly able to give the electron. If I talk about in the period, so since it's having the biggest size, it will be having the most metallic character, it will be more electropositive. And yeah, that completes my third point as well. And ionization energy, if I talk about the period, group 1 elements have got the least ionization enthalpy, least ionization energy, least in period because of the biggest size. Clear? So I have not discussed that in a detail because we already have done that. Just remember the tricks over here, the exact reasons should be there, right? So that you are able to, again, what has just come up in my mind is, some of the students what they do is, if they are getting confused in any one of these reasons, right?